Well, good evening, everybody. This is Dean, KK4DAS. This is the regular meeting of the Vienna Wireless Society Makers Group. It's the 22nd of January, 2025. And this is the second meeting in our series around building an SDR receiver. Of course, that's the end product, but the process is about learning to use KiCad to draw schematics, to do circuit board layout, to do circuit board production and assembly, and then ultimately connect up to the software on the computer for SDR. And Oliver Kilo India 3 Papa is leading us through this process, and so we're on the second evening tonight. Hopefully everybody's been working on their schematics and getting comfortable with KiCad schematic drawing. I know I did. Um, and yeah, so what we did in meeting one is we learned the basic interface for KiCad, and that video should be available online. I don't know if Jacek has posted it to the YouTube channel or not yet. I asked him to, so should be available online to look at and follow. And then the materials are available on GitHub, and you can find them there. All right, so with that, let me turn it over to you, Oliver. So please go ahead.
Right, thanks, Dean. Yeah, as Dean recapped, last time we did the schematic design. We learned how to draw the schematic in KiCad. This time around, we're doing the next step, which is doing the physical layout of that of all the components on a circuit board. Actually, doing this for this board is the work of many hours. So we're not going to do it all from beginning to end in this presentation or in this evening. We're going to get started. I'll show you how to get going, what my approach is to doing it, and then I'll fast forward through these various phases so you get to see the whole thing from beginning to end. But at some point, I'll wave my hands and magically skip forward in time, and we get a skip over many hours of work. But just your chance to ask questions as we go if something isn't clear. And then, we'll 2 weeks after this, we'll have another meeting, and that will be like, okay, now you've got a layout and a board layout. You actually want to have it made. What are the steps? How do you actually go about getting a board like this made by one of the board manufacturers? How do you get to the point of buying all components and getting everything in-house so you can start assembly? So that's what's to come next. So I'll start by sharing my screen. All right. Hopefully you can all see a browser. This is the VWS SDR repository on GitHub. You can see the link there in the top. I'll drop it into the chat so you can follow along. I'm not sure. I'm not confident I can figure out how to drop that into the chat. So I won't try and do that now in live. So that's where I posted the schematic that I drew. And that'll be our starting point for this evening. So the first thing we'll need, you'll notice if you go to the KiCad folder and look at the KiCad files that are there on GitHub, there is a folder called VWS-SDR.pretty. This is KiCad's folder structure, folder name for footprints. So these are what the component, the pads and the silk screen would look like on a PCB. So we have 3 custom footprints in this board that are all there, each one in their own file in that folder. I'll show you briefly how to import that now, but just so you know that they're available and you'll be able to use them and you won't have to redraw them yourself. Okay, so you open up the KiCad project. Open up the schematic. This is where we got to last time. We went through the steps of drawing this, fast forward to the end, and got to see the final product. So at this point, you have laid out the schematic, and you have gone through and you ran the footprint editor, and you assigned. Not footprint editor, I beg your pardon. You did the footprint assignment tool, which is this one over here, assign footprints. You ran that, and we decided, it again, hopefully it'll work this time. There we go. You decided what footprint pinout each of the components would have. For all the capacitors, all the SMD components are 1206s. There are a few here that do not have. Sorry, this is not behaving itself. Do not have footprints, so we'll just briefly do that. The first is this mouse is something's going wrong with my mouse setup. Hopefully, it's not going to be an issue today. So if you click on one of these pins, this particular component is a 14-pin connector. Hopefully, you all have had a chance to practice this, but you can find the appropriate footprint for that. That's a 14-pin one. Where is that? Connector, pin socket 2.54, 1x14. So I'm not going as slowly as I went the last time because this is kind of stuff we covered last time. So
Question.
Sure, go ahead.
Yeah, Oliver, I don't remember covering any of this. I got the schematic, but I didn't see anything about footprint creation. I guess meetings.
Maybe I dreamed it. I thought we had, but okay. So
we did a little bit of this. Go back and watch the video. I think you'll find it.
All right.
So I hadn't just click and drag these. So we'll see. And I made a clicked and dragged in the wrong place there, so a few got messed up. So let me open that again. So this is the 1x14 footprint. You know what? I am not happy with how this mouse is behaving. So I'm going to ignore that footprint for now. We're going to skip over that. But what we would have done is assigned footprints to all the components. You'll see from that review that almost everything was assigned. There were just a handful of stragglers. That isn't a problem. You don't have to get the schematic complete and all the footprints assigned before you go to PCB layout. Generally, it's a good idea to do that. But in this case, we're going to do it with some of the footprints still missing. So if you click this button on the top of KiCad, it switches you to the PCB editor. And when we gave the orientation the last time, there's a schematic editor and a PCB editor and a bunch of others kind of tools built into the KiCad framework. So if you switch to the PCB editor, it's blank. There are no components visible. It is entirely an empty canvas for us to start placing components and start routing traces. The first thing you want to answer for your board is how many layers of your printed circuit board are you going to use? You know, the very simplest circuit board is you just have the one-sided board where you just use a copper plane on the top of the board and you ignore the bottom. No one does that. The next simplest is a two-layer board. Imagine you've got copper on the top, dielectric in the middle, copper on the bottom. So you can draw traces or place components on either side of the PCB. That's the simplest thing to do, and it's the cheapest kind of board to have made. Generally, if you're trying to build more sensitive RF equipment where you've kind of got a mixture of RF and digital signals on the same printed circuit board, which we will have here, as recall, I'll switch this button, click this button to go back to the schematic editor. You recall from our schematic, we will have a microcontroller board, we'll have the Raspberry Pico on the same PCB as our RF electronics. So we've got this mixture of RF and digital signals. If you're in a case like that, you're best going for a 4-layer board because that helps you to maintain isolation between your digital and your analog domains and reduce crosstalk between traces. What does it mean to have a 4-layer board? It means you have 4 copper layers. Copper layer on top, 2 hidden copper layers in the middle of your PCB, and then a copper layer on the bottom that you can see. So if you go to a contract manufacturer, a board house like a JLC PCB, which is what we'll be using here, They offer a variety of standard 4-layer stack-ups as part of their manufacturing process. This is just Google JLC PCB stack up. You'll find a link to this site here. And so what we use is just this first one, JLC 7628 stack up, which has, as I described, a top layer of copper, thin layer of dielectric, 0.2 millimeters, layer of copper, more dielectric, copper, dielectric, copper. So those are the layers. You've got 4 copper layers. There's many approaches to what signals you put on what layer. I take a fairly simple approach, which is I have these 2 inner copper layers are ground. I don't route any signals along the inner copper layers. Inner copper layers are ground planes only. All my signals, all my power routes on the top and the bottom. But having these copper layers means that you can take one signal and route it over another, do traces through vias, and you won't have crosstalk between them because you've got that copper shield in between them. So that's the approach that I take. There's many approaches. I'm not claiming that it's the best. This is the best way. It's just the simplest way that works for me. So you've decided now on our PCB, we're going to go for a 4-layer stack up. So in KiCad, in the PCB editor, if you go to File, Board Setup, you can specify the layers of your PCB. What is it physically? What is a physical stack up going to look like? So if I go to physical stack up, see by default it defaults to a 2-layer board. Copper layers 2. So if you just click that drop down menu, see it's always an even number of layers. We're going to go for a 4-layer board, and it will add 2 inner layers. So the layer names are front copper, inner 1 copper, inner 2 copper, bottom copper. And if you really want to exceed expectations, you can make sure the layers of all the heights of all the dielectric layers are correct. It doesn't make a difference for the layout. It's just if you're wanting to make a 3D CAD model of your board to build into your CAD tool, and you would need the physical dimensions to be correct, then you would want to be specific about what those are. Again, switching back to the JLC PCB website, they tell you this pre-preg layer is 0.2104 millimeters thick. So you could put those numbers here in the dielectric thickness. This would be 0.2104 millimeters. And again, over here, and this middle layer is 1.065 millimeters. 0.065. So, so we've now, when we do that, it updates. And if we look at this drop-down menu over here, it tells us the lists of layers that we've got to work with. Now we've got front copper, inner 1 copper, inner 2 copper, bottom copper. So we've got 4 layers that you can switch between as you're doing your drawing and all of that. I'm just going to move this out of the way so I can see. All right. So we have we've specified that we want to go for a 4-layer board. We've defined that in the tool. Now we actually need to place some components. So the button you press, this is the button, this button here, which kind of like has half schematic, half PCB icon with a little arrow. This is update PCB from schematic. So what this does is it reads your current schematic file and imports all that information into this layout view that you can start placing components. So if you click that button, this window comes up. You hit update PCB, and it will place all the components on the board. You notice it threw some errors here. That's because we were missing those 3 footprints. So that's not an issue for now. We can define the footprints later, run through this process again, and I'll show you this later how you do this, and then bring those more footprints in, and it won't change the rest of your board. So we just ignore those errors for now. And it brings them in. I'm just going to click here in the corner to put them down, kind of out of the way. So there are all of our footprints. Job done. No, unfortunately not. Now the work begins. Now we have to figure out how do we place all of these physical components on the board. How do we lay it out physically on a board such that it makes sense? We can understand what's going on. We can assemble it. We aren't mixing up traces of different kinds, mixing signals. There's many ways that you can go about doing this. I'm going to show you the workflow that I go through, which works for me, but you feel free to modify it as you see fit. So the first thing I like to do is kind of draw a box of a PCB so I kind of have a space to work within, just so it helps me get a sense of physical size and in my mind lay out how everything's going to fit together. So the way we do that is we define an edge cuts layer. So if you go here to your layer selection and you go down here, there is a yellow layer that's called edge cuts. So this is the layer. This is the in the Gerber files that are produced. This tells the board house where to route their little CNC mill to cut out the edge of your PCB. Where do they have to cut all the lines so that your PCB will come out intact? So this can be, you can make wavy PCBs with wavy edges or circular edges or rounded points. You can draw this as complicated as you want, but for our purposes, I'm going to just click this tool over here, which is draw a rectangle, and I'm just going to draw arbitrarily anywhere on this canvas. Doesn't matter where. Draw a rectangle. Click once to start, click once to end. I actually want to specify the size of this, so I'm going to hit E for edit, and it will open up rectangle properties. So let's say it starts at, I want this to be 100 by 100 millimeters, and I'll explain why in a second. So I'm going to start at a point 150 and 200, 150. So now I have a 100 by 100 millimeters, which is 10 centimeters by 10 centimeters, roughly 4-inch by 4-inch PCB. That is, you can see my face on the screen, it's this size. This is a size that board houses like JLC PCB, they give you very good prices on your PCB if you can keep it to be this size or smaller. They charge you a much lower rate than if you had a larger PCB. So by sticking to the size, which is big enough for this project, we can get a PCB, a 4-layer PCB for about $1, $1.50, maybe $1.80 per PCB, which is a really good price. A 2-layer PCB of the same size would be 90 cents. So it's a 90 cents increase, roughly a doubling in the price, but it offers a lot of performance advantages in terms of noise. So I have placed my PCB edges. This is the space that I need to move all these components into, and figure out where to place them. So the approach that I take, and this is one of the things that KiCad makes easy, is I work with one block of the circuit board at a time. So if we go back to our schematic, hitting the schematic button here to switch back to the schematic, I want to start with this portion of the circuit and lay it out just by itself and make it a little group that is logically connected to each other. So it becomes like a Lego block on my board. And then I want to draw maybe this and make it its own Lego block, and then draw this and make it its own block, and then kind of figure out how they all fit together after the fact. So I want to start by doing the physical layout of these components on the schematic. The hard way to do this would be to look at this and say, oh, I need to find C1 and C2 and C3, and then switch back to the PCB and scroll through here and try and find C1, C2, C3. That's what I did at first before I learned how KiCad works. So don't do what I did. The easy trick is on the schematic. If you click and drag to select a group of components, I'll deselect the test point. So I've just got these components these symbols are all highlighted. If I now switch back to the PCB view, you'll see those same components have been selected in this tool. So if I just click and drag on one of them, I can pull them out of the crowd and they are now, I can kind of treat them as I can work with them as an individual block. So I'll just go back to the other board now and find, see this one, let's find this RF connector. So I'll bring the RF connector as well. So we're going to have the RF connector, and this is the local no noise amplifier. So, and all of its supporting biasing components. You'll notice KiCad draws these little straight white lines. This is the rat's nest. This shows you electrically what is connected to what from the schematic. The approach that I find to be best, and I think this is generally a good principle, is do the placement first. Figure out where everything is going to fit on your board and place it on the board. And only once you have placement complete, start drawing the traces to connect everything together. Because inevitably you'll decide, oh, I actually want to move this capacitor slightly this way or slightly that way. And if you then have to go back and redraw the physical copper traces for that component, you'll redo a lot of work. So first step is do placement on the entire board. Make sure you're happy with it. It physically fits where it needs to fit, and you like how it looks. And once placement is complete, then do routing, which is drawing the copper traces. That's step 2. So I have just arbitrarily in this corner of the board, I have placed this RF connector. There is the this is the LNA. RF in is connected to C1, so I'll just bring C1 over, hit R to make it rotate. I want it to be approximately centered underneath the RF in connector. A change I like to do, at this stage, I like to specify a fairly coarse grid, because components will snap to the grid, and it helps keep things aligned and makes it easier to align things precisely if you have a fairly coarse grid. And later you can make your grid size finer and move things if you want to. If I set this to be, say, 0.5 millimeter, now I've defined a fairly coarse grid, and you'll see as I move the mouse around the SMA connector, clicking and dragging, it does fairly discrete jumps. This is just helpful in making sure that my capacitor now, as I try and align it with the SMA connector, is actually precisely aligned underneath the SMA connector, just for neatness. I'm now paying attention to these white lines. It's helpful to kind of switch between the views. I'm looking at the schematic. Okay, the capacitor connects. Switch back to the schematic. Capacitor connects into the U1. This is the LNA footprint. So it can be helpful to switch between the views. So I don't see any need to rotate this yet at this point. The output of this whole circuit is capacitor is C4. It's connected to pin 3. Pin 3 is over here. Put these out the way. I'll take C3 and rotate it, hitting R on my keyboard. And there we go. Those 3 are lined up. You kind of have to, to get the best performance on your board, you do have to pay attention to what the purpose of these components are. So this is an RF trace that's coming in here. So I want this to be as short as possible. We don't want to have long meandering RF traces that will have a lot of loss. So that's why I've kind of placed them fairly close to each other, approximately. C2, if you switch back to the schematic, we can look at what C2 and C3 are. These are like decoupling capacitors that act as little charge stores. They charge up from the 5 volts, and they can provide current to the LNA as it needs it, and that current doesn't have to travel as far, essentially, as if it had come all the way from the 5-volt supply. So it's a good practice to have these decoupling capacitors as close to the component as makes sense. You don't want them to be a long way away because it's the inductive losses along the conductor between these capacitors and the component that's consuming that current. Those inductive losses can lead to basically generating noise on your power traces and your ground lines. So L1 is our RF choke inductor over here. But,
yeah, Oliver, on that
yep.
on that point, often the data sheets will even instruct you to place the capacitor or whatever right on the pin if you can.
Exactly. Yes. There many data sheets. Thank you for bringing that up, Nardine. That's a good point. I have some data sheets open over here. I don't know if the LNA data sheet has that in it, but many component data sheets will have a recommended layout. Typically, as you scroll towards the bottom of the PCB, or bottom of the data sheet, there will often be a recommended layout. I don't see it here, but that's something. That's a good thing to do, is to consult the data sheet, because they will often tell you, oh, particularly for RF components like MMICs, many MMICs, monolithic microwave integrated circuits, they will have a great amount of detail on what the best way is to orient the components around it to get optimum performance.
I might add as well, if you do have a trace length, that it has to be fairly precise, because it's a 50 ohm trace, and that's dependent on your substrate thickness as well as the
yes. Yes, that is something we will get to in a little bit when we get to actually routing the traces. Is how wide do you need those lines to be? And yes, we will get to that when we're done with placement. So I switch to the schematic. L1 kind of sits on this RF trace between pin 3 and the inductor. So roughly there-ish. C3 is not the right capacitor to put here. I need to have C4 here. That's why that's looking wrong. So C4, move that back, rotate it, put it in line. R1 supplies power to L1, and then I'm just going to put these two capacitors over here. If you want to, at this point, you see I've got some silk screens. This blue layer here is a silk screen. I have the component, the lettering for C3 is kind of underneath the footprint for C2, and that's no good because you won't be able to identify which is which when you're assembling your board. I find it very helpful, even when I'm in the midst of getting early in layout like this, is to switch to the 3D view. This particular view is, partially helpful. You can do things with the layers that are visible. You can manually edit which layers you can see. So I can turn off the copper layers. I can turn off the solder paste layers if I want to. There are also some presets defined here on the bottom right. So I often, when I'm doing layout, or doing placement, will use the all layers or all copper layers. And that makes it look a little bit simpler, particularly when you get into routing. Seeing all copper layers can be a nice way, because you just remove all that distracting. When you're doing routing, you don't care where the silk screen is going to be, or where the footprints and the outlines and the courtyards are. That's not really meaningful. So all copper layers is a helpful preview. Switching back to all layers here. But another helpful thing to do is you hit View, 3D Viewer, and it basically renders an image of your PCB. All those components are floating there in midair. But this is very helpful to kind of get a sense. I find it helpful to get a 3D view and say, oh, I see what size that is. Oh, that looks buildable. That looks about right. I don't think they're too close together. I don't think they're too far apart. I find it helpful to visualize the thing. So I will often switch to the 3D viewer just to have a look at things. And now I can see very easily that, oh yeah, I won't be able to see my C3 silk screen and my R4 and my C2. They're all jumbled on top of each other. Particularly as boards get more and more full, it can be hard to spot things like that. In this view, the 3D viewer makes it easier. So I'm going to move this reference marks around. See, this is R1, so I'm going to pop it over there. It can be hard when here I'm trying to click on C2, but if I click in the wrong place, I select, what's that? That is the fabrication layer for R1. That's not what I meant to click, and then I click over there, and now I've clicked on the copper for that particular pad. The trick in KiCad to select which layer responds to your mouse is, again, down here in the bottom right. There's the selection filter. At the moment, it's set to whenever you click, it will click on all items. And so you can unclick that and say, I only want to click on text. So if I click over here on like the copper, it isn't actually responding to my clicks because it will only find text, but it will C2, it will respond to because that is text. So that's a helpful little trick when you get to a crowded circuit board. It also allows you to do things like, for instance, once you've got a lot of vias on your board and you want to delete all the vias, you can, click the vias button, only select vias, and then you can click and drag over your whole circuit and it will only select the vias and it won't select any of your footprints or your traces. So that's a little editing trick, that workflow trick that makes life a little bit easier. So now I have laid out this LNA section. That looks about right. The components look like they all fit together. What I like to do at this point is select all those footprints. So left click and drag and right click. And now I want to group these together. So a menu comes up. Here's group items. So now I have a defined little block that this part of the board is placement is all completed, and I don't have to go and redo that. And as I do all the different sections, you can imagine I can figure out, maybe I can rotate the whole block and figure out how to fit it all into the footprint that I have without having to disassociate one component from the ones it's meant to go together. I found that to be a very helpful way of doing this. So let me put this back to where it is. So is that all clear so far? Is that making intuitive sense? Any questions at this point?
So when you were doing the layout, were you paying attention at all to the rat's nest, or are you just ignoring it?
I was largely ignoring it. I knew from the schematic, and so I switch back tab back to the or tilde back to the schematic. I know that C1 is looking at the schematic. C1's connected to U1, and then switch back. Where I was paying attention to the rat's nest was as I was rotating the components. So if I double on a group, if I double click, you now can go into the group and start editing the contents of that group. So that's what I'm going to do now. So if I do this the wrong way around, I can see that the rat's nest lines cross over. Then I say, oh, this component is not appropriately oriented, and so I can hit R to rotate it. So at this point, I'm usually only paying attention to the rat's nest for that purpose, to make sure I've got the orientation right. I'm largely just looking at the schematic and seeing, oh, this component needs to be close to this component, and then the rat's nest will just help me visually see which pin is connected, which pad connects to which pad.
Hey, Oliver.
Yep.
So we're really in the deep end of the pool here. And we're starting with the T41 receiver, which is pretty complicated.
Mm-hmm.
I thought last time we met, when you were looking at a data sheet for that little 5351 breakout board, or
Mm-hmm.
the 5351 chip.
Mm-hmm.
I thought in the data sheet you saw a recommended how you would make your own breakout board actually.
Yes.
Did you? Well, I've got the data sheet here and I can't find where you found that, because I was thinking to learn KiCad, that would be way easier for me, just to see if I could reproduce that little breakout board.
Yes, and I did. I have been thinking about that. This is this is a fairly complicated board. You can learn if you manage to get through this, or you can get a KiCad merit badge of a tremendous achievement. But hopefully, what I'm doing here is showing you how to work with the tool. You can pick a simpler schematic if you want to build it at home, and the thing that we build at the end of the day will be this reference schematic. So you won't necessarily have to build the one that you have laid out yourself. So don't feel like you have to complete it
Oh, sure,
to
sure.
succeed.
No, my question though, I thought you showed a simple circuit in the 5351. Well, I've been through all 33 pages of that, and I can't find what I saw. You had it on the screen, but
I think this is this what I had on the screen?
well, no, I mean it was a little circuit diagram.
Yeah, yeah. I don't recall exactly what that was.
I thought it was in the data sheet for the 5351, the recommended.
Yeah. I don't recall that exactly. I could Google it and search for it now. We are going to use this this breakout board for that Adafruit is produced. The equivalent circuit is on the T51 RF board, and it's a lot of this stuff on the Adafruit is more about logic level shifting. So it's 3.3 and 5 volt tolerance. So many of these components are unnecessary. If you're doing it yourself, you can build a simpler one. You only need a couple of capacitors and the crystal, and that's about it. Pull up resistors
Well,
if you want.
Go ahead then. I was hoping. Yep.
Yeah. Sorry, I don't recall exactly which one it was.
Okay.
So there I did. I placed all this particular block, and I have it as a Lego block. And at this point, I will then switch and do the next part of the circuit, and I would say, okay, now I'm going to take these components, click and drag, select them all, and zoom out and just drag these all and physically orient them all close to each other. And like I said, we've been going for 35 minutes on this now, and we've done this little portion on the board. So this takes a while. I'm doing a lot of talking, so that slows us down. So rather than continue and physically do this, I'm going to fast forward to where I've done all the placement, and all that is placed on the board, and we can just move on to the next step, which is once you have a placement complete, which would be routing. Okay. So through the magic of Git, I'm going to tested this before and it worked. So fingers crossed it's going to work again. Okay, I'm just going to close this and then open it again. Where did it go?
So what he's doing here is he's using the Git tool, which is basically a management tool for keeping track of your version control, to switch to the version that he's already completed.
That's right. Thank you for elaborating on that, Dean. Yes. So I did all this work before and saved my work as I went along using Git version control.
Git is not part of our project, though.
Yes,
that's just something that he's using to do his own management.
Yeah. And Git works if you are into version control. Git works very nicely with KiCad because all these files are text-based under the hood. They aren't graphics. So Git version control works very nicely. So you'll see that I have now all those components that were there. I have laid out on the board. See here, if I click here, here's an RF gain block. I laid it out slightly differently. I think if you laid out the same circuit 10 times, you would probably come up with 10 different layouts. Just depends on what makes sense to your brain at the time. Probably if I was better at this, it would be the same every time, but I am what I am. You'll notice one thing I've added is a lot of silkscreen art. So if I switch here, I can turn off the rat's nests. That's another thing to show you. On the left here, you can click that little button and the rat's nests go away, which makes it a bit nicer to look at in your PCB. Rat's nests are going to be very useful now when we do routing. But let's just look at see where we are now with where we got to with placement. If I do view 3D viewing, this is kind of like the physical layout of the board. I've placed everything. I've tried to space these surface mount components well enough apart that it's going to be easier to do from a surface mount soldering point of view with tweezers and a soldering iron. I put a lot of silk screen art on there, just literally drawing lines in the silk screen layer and adding text. So you can see this block is the RF gain block, this block is the Taylor mixer, here's the low pass filter. I find it helps a lot with debugging to find out, you know, what is what and what connects to where. Every pin is labeled, so you know this particular pin on the PCB has this function, particularly for all the breakout pins, and you aren't having to find the data sheet or have a printout of the data sheet to remember what each pin is. So it's just you will thank yourself in the future if you put a lot of silkscreen art on your PCB, put your notes on the PCB, and make it as self-documenting as possible. So that's what I've tried to do here.
Quick question, Oliver.
Sure.
Those capacitors and resistors, are those like 0805s or 1206s?
These are 1206s.
Okay, good. Thank you.
Yes, yeah, we've gone for the easiest to solder. Not that it'll be easy, but the easiest to solder. And similarly, we picked these op amps and components that they have a wider pitch spacing of their pins, so they're easier to do with the hand.
I prefer 1206. So they're like 1/8-inch resistor sizes. That 8 watt resistor sizes for axial, pretty easy to use. And by the way, just to let you know, I am following you. I finally figured out how to at least put the footprints on the individual components. I'm sure the video will show the rest.
Yes. Yeah, this is why we space you these 2 weeks apart. There's a lot of time for you to practice what you learned. So anyway, so that's what I came up with for the placement. So the next step is routing. So as someone pointed out earlier, it's a good practice to have 50 ohm traces. So at least your trace impedance of your little transmission lines on your board don't cause discontinuities. In reality, this is an HF board. The physical size of this is, it's a few inches. It is a very tiny fraction of a wavelength. So if you hand waving these things, the trace impedance doesn't really matter if the physical thing is that small. It matters a lot more when you get up to VHF, UHF, and definitely into the microwave. Then you can't ignore this at all. At HF, you can get away with with many sins when it comes to trace impedance, but we'll do it the right way. So if we go back to the JLC PCB website, they tell you this is we're going to have traces that will be running on this top copper layer or the bottom copper layer. So both of those layers, it's symmetric. It's 0.2 millimeters thick, and it's on this material. The material is 7628, which is a particular type of material called prepreg. 7628. They have up here 7628. They tell you what the dielectric constant is. It's 4.6, which is the same as basically as FR4. So if you know the thickness and you know the dielectric constant, you can calculate what the appropriate width is for a trace that would have a 50 ohm impedance. So they have an impedance calculator very helpfully on their website, which you can use. So we'll use that for this. KiCad also has an impedance calculator built into it if you wanted to use that instead. So if I, let's go here, impedance and trace width, I want a 50 ohm impedance line. It's a 4-layer board. Overall thickness is that. It's the outer layer. Okay. And then I just click single-ended outer layer, and it's telling us that if we go for the 7628, it says we should have a trace width of 11.5 mils, which is not millimeters, it's thou. It's thousandths, 11.5 thousandths of an inch. I don't know why this is the bane of my existence, that you have millimeters, which is metric units, and you have mils, which is not metric. It's not millionths, it's thousandths of an inch. I don't know why they're called. If anyone knows why mils are called mils and not thous in the PCB world, I would love to hear that. But long story short, if you convert that into sensible metric units, that is it's 0.368 millimeters. So I previously calculated that.
It's an English thing. Nothing. There's no magic as to why they do it. It's just metric versus imperial.
Yeah. So here on the left, you can edit under this little box over here in the top left. You can find the same. You can find it elsewhere as well. If you go to File and you go to Board Setup, you can define like predefined trace widths. So it helps you when you're doing the routing to easily change in different trace widths. So I went to File, Board Setup, over here where it's predefined sizes. There's tracks, pairs, differential pairs. You can get very complicated. For our purposes, I just hit that plus button, and I added a 0.368 millimeter track width, which is the 50 ohm impedance. So I had previously done that, so I don't have to do it again. So I now know when I'm in the routing tool, I'm in the routing phase, I can select that 50 ohm impedance and go with that. So the way you do the routing is you change to the copper layer that you're wanting to draw your physical copper traces on. So in this case, I want to go to front copper. On front copper, so I'm on the layer that I'm actively editing. It's a front copper layer. I want to use, I go to this menu over here, I select the 0.368 track width. And over here on the right is the kind of drawing tool you want to use. And what I want to do is route a track. So basically draw the little wires on the PCB. So if I click on that,
you've already decided that like this layer is going to be your RF layer, and then the other side is going to be your digital side.
It's going to be a bit of a mix. I will have some digital on this layer. I might have some digital on the other. There's many different philosophies for approaching like what you route first and in what order you route things. I like to route the most sensitive traces first, the ones that have to be the most intolerant of imperfection. And so I start with the RF traces, and I want to make sure all the RF is traced out first. And I don't have not been forced to route RF via some non-optimal route because of some previous traces that I had put there. So I like to start with RF, then I will do digital signals, and then I'll do power and everything else. So that's the order that I like to approach things. Others may do things different. So I'm going to start with the RF, and I've already decided arbitrarily, since all the components on the top, these are SMD components, we have put everything on one side of the board. We switch here to View 3D Viewer. These are all on the top side of the board. There's nothing on the bottom. There's just going to be traces on the bottom. There won't be actual physical components. So all the RF traces will be on the top side of the board. That's complete. So I have the route track selected, and then I just start at the RF input. I say, well, there's pin 1. If I move my mouse over that and I left click, it now helpfully highlights, you know, where all the other pads that it has to be connected to. And as I drag down, it will show me the trace. And so I clicked on that pad and it filled it out. And so I go to the next pad that goes to the LNA. This is the output of the LNA. It's going to go here to this pad. Output of the decoupling capacitor or the DC blocking capacitor goes to this input of the Taylor mixer, etc., etc. And so I can this point I see the Taylor mixer. They're all you know. I'll come back to all the internal traces of the Taylor mixer. I just focus on the output, and I looking at this rasterness, I can't tell which one of these which one of these is the output conductor. So the helpful trick here is to switch back to the schematic, which I actually don't have open. So open the schematic view. I find the particular trace on the schematic that I am wanting to draw now in the PCB view. If I move my mouse over it and I hit the tilde /backtick key, which is the one just to the left of 1 on my keyboard, you'll notice that when I move the mouse, I didn't click, I just moved the mouse over it and hit the tilde button. It now becomes highlighted pink. And that, when I switch now to the PCB, eventually, it's now highlighted all the pads that are connected to that particular net. So that helps to pick out, where you're working as you move between the schematic and the PCB. So, see if this needs to go over here. I'm just going to very roughly draw some things in here. Hey, how about I pick that up as well? Switching back, I'm going to select this other trace. So hit the tilde, now it will highlight this trace on the schematic. Switch back to the PCB. I see that this one is, I need to connect these two pads to this pad. So this point, now I've noticed that I have these traces have crossed. So you've got a couple of choices here. Easiest thing to do is route the trace and switch between the layers of the board. So I'll show you how to do that. So I'm trying to connect this pad over here, pad 2 of this capacitor, to that pad over there of the mixer chip. So I left click and I start routing the trace. If I wanted to, I could just have the internal algorithm in KiCad try and figure out how to connect the two, but now it's come up with this monstrosity of a trace that's going to cause me problems later. So rather than do that, I get approximately close, and now we can use the magic of vias to switch between the layers. So if I, without clicking any buttons, just press the V key on my keyboard, it will now place a through-hole via that will take us from the top layer of the PCB to the bottom layer of the PCB. So I now click to place this via here, and now it's drawing a green trace, and green is the color for the bottom copper layer. So now this trace that we're drawing is on the bottom. Hit V again, and it will give us a through-hole via to come up to the top of the PCB, and I can complete the circuit. So, that's one way of doing it. Probably will work fine. Given that it's an RF trace, you want to minimize vias in RF traces. So I don't actually, looking at that now, I don't want to do it this way. I want to delete this trace that I've just drawn and delete this other trace so that they don't have to cross each other, and I don't have to have my RF trace going from the top layer of the PCB to the bottom layer of the PCB. That can be problematic. So that I purposefully did this wrong so I could show you how to undo these things and show you some tricks there. So if I click on a trace or click on any one of these traces and I want to delete all the sections of the trace, the hard way to do it would be to click, delete, click, delete, click, delete. And that's the hard and tedious way. The easy way is to click on the trace and then hit the U key on your keyboard, which is like up, up, it's U for up, just increase, also select all the bits of section that are next to this. So if I hit U once, it will select that section to the right. Hit it again, it's now selected the rest of that trace, and now I can delete all of those with one key. It's much easier than trying to click on each one and delete them manually. So again, hit U to delete those, and I can redo this trace. And now I've decided actually I want this one to come like this, and I will take this one over there, and that way they don't have to cross each other. They don't have to have my RF trace jumping between layers. Another easy way to highlight what kind of routing to do is if I move my mouse pointer over a pad And again, go back to that tilde button. If I hit the tilde button, it now shows me all the pads, all the other pads that are on the same net. So, oh, now I can see very easily via this highlighting that this pad needs to connect to this pad and also to this pad. And then I can
I'm
move
sorry, what button did you hit there?
it's like the tilde / backtick button,
Okay,
the one
yep.
to the left of 1 on
Thank
the
you.
keyboard. Yep.
All right.
So if I move my mouse off and hit that again, it deselects it. And so that was nice. That's easy. And then I can just, just keep going that way and so forth and so forth, continue through this. So while I gather my thoughts, there was one more thing I wanted to point out in the section. I'm trying to remember what it was. Any questions while I try and remember what I was going to say next?
I know that some of the tools have like an auto route tool. I presume this one has as well, but my guess is with something this complex, it's probably pointless.
You are correct. I have not used the auto route in a long time. Don't remember how to find it. But yeah, there is some level of auto routing available. But because I haven't used it in such a long time, I can't point you at it. Particularly if you're doing RF circuits or mixed signal circuits, where you care about these things, you really don't want to trust auto routing because it doesn't know what's what, and it will make some poor routing decisions.
I was just going to say that, Oliver, because yeah, typically with RF, you don't auto route.
Yeah. Yes. Tia, you had a question.
Yeah. So I saw how you would route the wire under the board in order to make stuff not cross over, but then you decided that that wasn't a good idea. Why isn't it a good idea to have stuff go under the board?
It wasn't a good idea for that particular trace because it's an RF trace. It doesn't really matter at HF frequencies, but particularly as you get to higher and higher frequencies, just the physical act of transitioning from the top layer of a printed circuit board through the circuit board to the bottom can have insertion loss and discontinuities that are bad for RF signals. It wouldn't matter at DC. It honestly probably doesn't matter at HF either, at the frequencies we're working at here. But certainly when you get up to much higher frequencies, traces that carry high frequency signals, you want to avoid transitions through vias as much as possible because it's hard. You end up with impedance discontinuities that can mess with your signal propagation.
So essentially high frequency reliability concerns?
Yes. And that really starts to matter when you get up to the hundreds of megahertz. Waving my hands very roughly, it's in the hundreds of megahertz and higher that really starts to matter. This circuit will work entirely at frequencies below 30 megahertz, so it honestly doesn't really matter for this. But it's good to have good practices and build good habits when you're doing these things. Okay, so yes, I remember now the other thing I was going to do. So you laid out all your copper traces. Let's assume that I've done all that. I'm going to skip over doing the rest here. The next thing you want to do is lay out your ground planes. So over here on the right is a little add filled zone tool. So what I'm going to do with this is I'm going to draw a rectangle and say, I want you to draw a plane, a copper plane, that you will fill in and fit around all the other stuff that's already drawn on the board and attach it to this particular net in the schematic. So this is an easy way to fill those two inner layers of the PCB and then all the empty space in the top layer and the bottom layer, fill that all with copper, and then we'll put some vias in to tie it all together so we have nice solid ground in the next step. So again, here on the right is this add filled zone. Click on that. And now it's, you can draw whatever shape you want. I'm going to draw a rectangle. So you draw it one vertex at a time. So click in this top left corner, and it asks you, before you draw the rest of the shape, it asks you what is the shape that you're drawing, what layers of the PCB are these shapes on. So I want this to be a rule, a shape filling rule that applies to all 4 copper layers, and I want it to be connected to the ground net. So now it's going to make this a ground plane on all 4 layers of the PCB, that it will fill it in automatically. So, okay, now I can continue, zoom out, scrolling the center mouse button, zoom in again to hit the other vertex. You don't have to be precise. I could be off the PCB like this. It just looks neater if it's precise. And then the last vertex, you double click. So now it has filled out. It's now got this rule area that it's added here. You'll see it's got this funny like stripy edge to tell you what it is. And if I hit the B key on the keyboard, it will now do the logic of drawing this ground plane all over the PCB. So if I hit the B key, and it will build the filled zone, and now I can see that there is, it has filled copper in on the top layer. Everywhere where there isn't already a trace or a footprint, it has now filled in with copper, and it's observed whatever the distance rule is this particular net had for how far it gets up to the edge of that particular trace. If I look at the inner copper layer, we can see that that is basically solid copper, except for all the vias and through-hole components are. The next inner copper layer is the same. It's also solid copper. And then the bottom copper layer is similarly.
So look at your upper left again. So what was it, like C2 and C3 are both connected to ground, if I remember from the schematic, right?
Yes.
So that makes the ground connection when you just did that?
Exactly. Right. It knows it at the same net, so it puts these little thermal relief. It doesn't connect you solidly to ground, because that will be hard to solder, because the ground plane will be sucking all the heat away from your soldering iron, or from the it messes with reflow soldering as well. So it's just kind of the default rule will have those little thermal relief spokes to connect the pad to the ground plane. You can change that by click on the component and I hit E for edit. Over here, you can do clearance overrides and settings. If you wanted to, you could say the connection to copper zone. You could say this by default uses the zone setting. It's whatever we have defined in the default rule set, and whatever comes with KiCad is fine by default. So you don't have to configure this yourself. But if you wanted to, you could say, oh, I want this just to be solid. I want this particular component or this particular footprint to have no thermal relief. Hit OK. And then when I reflow, when I hit B to redo the filling out the ground plane, it's now a solid connection and there's no thermal relief. And then I will be kicking myself later because that will be a very hard capacitor to solder. So that's how to quickly do filling out the copper ground plane. The next, so when you do this, there's a variety of videos I'll send around emails afterwards that really explain the benefits of putting vias in to tie your ground, to tightly couple your ground planes together. So if I just, here on the right is a button for a via. So a via is a little hole drilled for the printed circuit board that's plated, so it's got copper, so it's like a solid conductor going through your circuit board. So if I select that and I place it somewhere on the board, I'll zoom in now, you can see it's a ground via. So this is now an electrical connection between all the copper layers of the board, all the ground layers, and all 4 layers. This is now an electrical connection between them all. So you should go around and put many vias on your board so that the ground lines are all connected together. Careful you don't click on a trace and accidentally ground a trace. It's a good practice for components like these that are connected to ground to put vias, at least one via, close to the ground side so that they have a nice electrically short connection to your ground planes. It matters a lot more up at RF frequencies than it does at HF, or at higher frequencies than at HF, but it's still a good practice to have.
Typically, you like to heat for higher frequencies. You got a rule of thumb is like between a 16th and an eighth of a wavelength between the vias.
Yeah. So if you apply that to HF, we don't need any vias on the board because it's such a small fraction. But still, it's a good thing to do. It's a good thing to do. There's a much easier way to place a bunch of vias. You can do plugins in KiCad. There is one particular plugin that is called, you install the plugin that's called KiCad Action Scripts. So KiCad-Action-Scripts. If you go to the KiCad, the main project window, and you go to Plugin and Content Manager, click on that and wait. This is part of the KiCad official repository. If you search for this KiCad-Action-Scripts, this is a script that will help you. There's a bunch of scripts. There's a lot you can do with scripts and with plugins. They help tremendously in KiCad. But to keep this simple, this is the only one I'm going to use. And in particular, what we want is the via stitching plugin. So once you have this installed, you restart KiCad, you will find that this button over here gets added to your toolbar, which is the via stitching generator. So if you click on that, it will launch launch a little tool that will go and will place vias all over your PCB. So you just have to tell it the parameters of your via. Defaults are fine. We want these vias to be on the ground net, and we want the grid size to be, how far do we need these to be? So I'm just going to say arbitrarily, 5.08 millimeters is just a multiple of a 2.54 millimeter standard spacing size. And if I hit run, it will now place a very nice grid of vias all over my board very smartly. If there's a component in the way, or a trace in the way, it won't place it. And so that's a nice quick way of placing all the general grid of grounding vias for your PCB, and that will save you a lot of tedious clicking around and placing of these arbitrary stitching vias. Yep. So obviously I'm not going to do the rest of this because we've already hit the time, gone over time, and there's hours more work to do on this. So what I'm going to do again is do the magic of using the Git version control to skip ahead to where I've already done all that. Stash, switch. So now I have skipped ahead into the future where I've done all that work. PCB tool, open up the schematic, open up the PCB. So now I've done all the routing. Show you the 3D view of that. That's what it looks like. Kind of what we saw before, but now you can see all the traces running between all the components. You scroll around to see the bottom side. You'll see there's just a few signal traces in the bottom side. Largely, the bottom side is these big fat traces, which is the power distribution. Don't need to be that wide for the current that's been drawn. This is going to be a low current circuit, but it just reduces the inductance of those transmission lines. The wider they are, the lower their inductance. So anyway, it makes life a bit proper RF designers or circuit engineers will tend to have power planes. They'll use one of those inner layers of the PCB as a power plane. So there might be one entire copper layer that's a 3.3 volt layer, and another layer will be their 5-volt layer. And so if you have a component that needs 3.3 volts at, say, one of its pins, you just put a little via next to it and say the 3.3 volt via, and then it will just pluck the power out of the 3.3 volt plane and use it. So if you have many layers to play with in your PCB and you're doing this professionally, you can do things like that. But for the purposes of a rank amateur like me, I tend to keep my signal traces on the top to the greatest extent possible, keep my power traces in the bottom, but it's just a general principle. It's not a hard and fast rule. So at this point, I wanted to show you something about the workflow in KiCad, that it's not just linear one way from schematic coming to here. Let's say we got to this point and we decided, you know, we want to change the schematic. What I really want to do is add a component to the schematic to basically give me, I don't trust that I'm going to be able to solder the RF amplifier accurately. So I want to put a little bypass jumper in, that I can just have a little jumper that I can bypass the RF amplification stage just for the purposes of testing as I'm building my board. So you can go back to the schematic and you can edit the schematic, and you know, you don't lose all the work that you've done before. So you can do the usual thing on the schematic, which is place, add symbol. I want to put a, let's say a jumper, search for the jumper. Here's an open jumper. I'm going to add it. Just going to use it to basically bypass this entire LNA section so that my RF can go straight into the input of the mixer. I need to assign a footprint to it, so I'm just going to edit it, hit the E button, go back to the footprint window. If you've been following along on the schematic, you would have done all this before. This will be the easy workflow. So, and I want on I'll do it the hard way because I can't remember what that is. It's connector. Too many footprints. Pin header 2.54, and I want the 1x2 pin header vertical. That's the footprint that I want for it. Okay. Okay for that. Now, if I switch to the PCB, that component is not present, but I can update the PCB from the schematic. And what it will do is everything else will remain unchanged. I just have a new footprint now that I can place wherever I want. So I can kind of figure out, oh, I think I can fit it in, say, over here. And I can then, you know, route some traces to do this quick and easy, and then hit B to refill the PCB. Now I've added this component. So it is possible to go back and edit and change and flow back and forth. It isn't just a once and done, and you have to do your work all over again. So it is also possible to go in the opposite direction, though I don't recommend doing this, and I try to avoid it at all costs by deleting a component on the PCB. And then when I switch to the schematic, there is an somewhere here, I can't find it right now, there is an update schematic from PCB option as well. So you can kind of bring some of those changes from the PCB back to the schematic. I don't like doing that. I recommend that you don't do it. You lose track of what I like everything to flow from the schematic and flow through to the end. So I'll just get rid of all that. And so that is where that is the layout that I came up with for this board. The next time around, we'll go to, okay, so now you've done this layout, now what? walk through the manufacturing steps. But I know we've gone over time already. This is a lot to get through. This is arguably a lot more complicated than the schematic side. So more questions.
I was just gonna say I figured that out, Oliver, when I was, because I didn't know how to put the footprints in, but I figured out on my own how to get them. And every time I did an update, I just did exactly what you just did, and it created a whole bunch of errors. But all of a sudden, that one footprint showed up.
Yeah.
So.
Yep.
Well, Oliver, thank you so much again. This is great. Again, it is an awful lot to take in. I'm starting to wonder if maybe for this particular part of it, we may want to actually go back to a simpler example at some point so that we actually can kind of do. I'm probably going to do that myself. I'll probably just build a small amplifier or something like that and see if I can do it just with a small board.
I think that's a good idea, and you can use the schematic that you drew for this, and just copy out only the say the just this section, and copy out just this amplifier section, and make your own little 21 dB RF amplifier on its own little standalone board. Copy this section out, put a little SMA connector on the other end, and now you have your own little amplifier board. You just need to add some kind of connector for the power rail, and it might be a simple thing to do.
I might add, Dean, that would be a good thing. That would just be a good project in and of itself, just have an amp for doing some breadboarding or other stuff too. So
yeah, no, that could be really, really good. And then for the other projects I do, I have a lot of circuits I tend to use over and over again.
So Oliver, I have a quick question.
Yeah.
We have a 4-layer board, but the two inner layers are both just solid grounds, right?
Yes.
Is that just because that's the way they typically are made? You wouldn't buy a 3-layer board?
Yeah, it's because the way they're made that it's like 3 separate PCBs sandwiched together, and obviously copper layer touches copper layer, and so that's a single layer, and so you'll end up with a 4-layer board. And what it allows you to do is have, so this is hard to see in this view. If I switch this to all copper, it's harder to turn off that. Hit that button over there on the left, and that turned off the copper fill, so you can see is I can have some high-speed digital lines. These are GPIO pins, from the Pico that are going to this breakout. And if this was a 2-layer board, if I'm looking at the bottom layer, I've got my power trace. Because if this was only a 2-layer board, I would have my power trace running directly underneath these digital lines, and you cause yourself all kinds of problems with coupling in that case. All these digital signals going across these lines would be coupling into your power, causing you trouble. But having a 4-layer board, there's actually 2 solid copper layers between that bottom copper trace and these ones here. So it allows you to get away with a lot that you wouldn't otherwise. And similarly here, I've got these are the SDA and SCL. These are the I2C lines coming over here, crossing over some RF lines. So you wouldn't want to do that on a 2-layer board. Have a digital line break the ground plane of an RF line. That's the rest.
So what does one of the middle layers look like?
So if I turn this on here, there's inner copper. There we go. So that's what the copper layer that's underneath the top layer. That's what it looks like. So it's basically solid copper, except for where the vias are and the through-hole components.
Okay, cool.
And I think one other quick one. When you went and added your component, is there a way that you it'll redo the vias to avoid what you added?
Yes. So you can click on any of these vias, and it will select them all as one group. They are grouped together automatically by the tool. So I can delete them, and all the vias are gone, and then
just redo them.
Okay. And then redo it at 5 millimeter spacing.
Okay.
That part is easy. And you'll notice now that I've got more on this board, you can see that it was smart enough not to put any vias. It hasn't shorted out any traces with the vias. It avoids that. It avoids it better than I avoid it when I do it manually.
All right, I'm going to use Maker's chair prerogative and call it tonight. Oliver, thank you so much for everything tonight, and thanks everybody for participating. I'm going to stop the recording now. We can continue to chat a little bit if you want, but this kind of concludes the formal meeting. So I'm going to say 7 3s for now.